Hi everyone, my name is AtibaGriffith and I'm from the Department of Economics at the University of the West Indies, KFO campus, and I am a final semester PhD student working in the area of computational and complexity economics. What we have graphed before you is a geometric Douglas production function, and to highlight some of the features of the graph, on the yellow line, that is basically our 45-degree reference line that allows us to know where we are in the Cartesian system. The blue plot is our logarithmic growth pattern, a typical growth pattern regularly used in growth systems in economics. And the black line is a reference line, or what we call a boundary line, to know where we should be on our limits for our input and output production systems. The red line, however, is the input for labor, or what we call the input for the driving force of the system. And with that input, it produces an output, which is then synchronized somewhat by a delayed reaction between the red and the green lines. And then the purple, of course, is our capital input variable, where we basically inject capital into the system to make it viable over the time period. On the next slide, however, we'll go more in depth on how this system actually works and also how the multidimensional part of the system is captured and simulated. As mentioned on the previous slide, I will now go on to show you how the multidimensional properties of the geometric Douglas production function is interpreted by the analysis we have developed at the KFO campus in the Department of Economics. So what we have here is a setup of what we call the input-output system and the growth patterns of that system, along with the stochastic noise that we will show you eventually. So far, being that it's geometric, we mean that we're going to be using angles and trajectories to actually interpret the data. So for our references, we have our 0-degree line, we have our 30-degree line, our 45-degree angle line, our 60-degree angle line, 90-degree angle, and so on around the whole geometric compass. To basically simulate the system, we generate what we call a force function, and that allows the system to actually run. And you can actually see the movement here in the system. Along these lines, what this is basically the contraction and expansion of the system over time. And that allows us to capture the noise and also the patterns of the system. So let us take a look at the different dimension of this system, and when we turn our system, we can actually see the noise that I'm talking about. Now, these green lines that you're seeing is actually the vector points of the system, and that allows us to know the angle and also the amplitude of the system, and you will see that it will contract and expand at some point. Now I'm going to pause the video here, and you will see that there are some smaller and some larger. So basically what you're seeing is that the information is transferred from the input system through to the output system, and that will give us a pattern, growth pattern. And you can see that here with my cursor is actual growth pattern here. These solid red lines that you're seeing here is actually our boundary lines that we had on the previous graph. And if I go a little further, we will also see that those red lines actually produce a next growth pattern. Behind all of this, however, is the stochastic noise we were alluding to earlier. And our aim is to develop a filter that will filter out noise and allow us to have a cleaner example of what we call a typical geometric multidimensional input-output Douglas production function. So far what we have done, we have generated a geometric system with over 5 dimensions, and the hope is that we'll be able to develop a control system for this system developed at the UE campus of the University of the West Indies.